Hey, and welcome to Saturdata. This is a special edition Saturdata where we're going to be looking at a SQL notebook. Again, I'm Sam, and Schiff has done a couple of the other notebooks for this season. And we wanted to take this direction because we thought, we spent a lot of time yapping about some of these really cool topics. And one we're going to talk about today here is SQL and DuckDB. But we said, why don't we dive in a little bit deeper, right? And you don't have to go somewhere else. You should go somewhere else. But you can also look at the way we approach code, the way we approach notebooks, the way we think about things, and how we walk through them. So we thought that would be really beneficial for some people, and we've gotten some requests for that. So we wanted to make sure to run through some of these. So today, like I said, I'm going to be talking about SQL. Try not to bore you. In the probably 45 minutes or so it'll take for us to cover this notebook. Today we're going to be talking about the New York City taxi data set. It's one of the easiest taxi data sets to work with. It's available in the repo. If you pull the repo down, we've included 2 Parquet files in there for you. So you should have the data. If you just clone the repo, pull it down, and away we go. All right, so first up, we're in a Marimo notebook right now. The way I got to this was in my project actually doing the UV edit or UV run Marimo edit for this specific file, right? And so I'll pull that back up just to demonstrate, right? How I got to that point. So you see here, I'll quit down there in the bottom in the terminal, and then the tab complete worked there because I had already created the resource C. So even we can mess some of these things up. Okay, we're back to it. So resources, season 1, SQL resource. You have the intro here, which we'll just look at in the markdown. The SQL for data people. We're going to talk about DuckDB. We're also going to focus a lot on DuckDB with NYC, Traxi data, their taxi data. And we're going to talk about some of the differences between DuckDB and SQL or Postgres. I got to see Hans, who's one of the creators of DuckDB at Day-to-Day Texas, and his talk was awesome. And one of the things he really focused on with DuckDB was the joy of programming, right? And the joy of being able to use these tools. And a lot of these tools don't bring joy. They bring frustration and anger. Make you want to throw your computer out a window. And really feel like with this Marimo DuckDB combination, you're leaning into that joy piece a lot more. Like you work in this and it feels nice, especially if you're not a sociopath and you work in dark mode. Just kidding. But here in the introduction, right, we'll just talk a little bit about what we're gonna do, right? Loads in some of the data, talk about the window functions, advanced DuckDB commands. Don't be afraid of the word advanced. It's just DuckDB. We'll run through some of those commands. CTEs, subquery patterns, common table expressions are what CTEs are, subqueries, pivot versus unpivot operations. Great, right? Directly available in DuckDB, not previously available in really any ANSI SQL. It's not supported in ANSI SQL. Advanced SQL patterns, idempotent operations, performance optimization. So let's go ahead and run. Obviously here you can just run through, but I would encourage you to look at some of the things we're doing, especially here with the directories. If you're working in Python, right? If you're working with files and you're working on a team that is also working on the same files, so you're working in a repo and you're storing data in the repo. You don't normally store data in the repo, but understanding these file access patterns are really important 99% of the time, right? Because you're gonna have some reason you need to do this. Now, if you're just a pure SQL analyst, right, it doesn't really matter, right? They're gonna tell you where the database is, schema is, and tables are, and you go pull them away. I wouldn't make a big deal about it, but just depending on your profile. We're loading in some of the packages, right? Marimo, Polars, PyArrow, DuckDB. So we're gonna look at it. But that environment setup is complete. Database setup with DuckDB. So as you can see here, we create the connection with DuckDB in memory, and then Marimo is going to automatically discover this connection that we create. So this is kind of how the two play nice together. You initialize that session, and then now as we do mo.sql in the future, Marimo is going to automatically discover the connection variable that already exists. And so we're going to run that, and we're going to see that pop up. Yep. It just means what it's telling us here is that the connection happened, and we even see the test result, right? With the con.execute, the con was created here in line 10. So we have now a database operating in memory, which is, again, just the joy word here really applies. The reason we loaded in polars, we're loading in the data with polars. Now, we could do this with DuckDB as well. Just trying to show how these tools also can be paired together, right? But pretty sure DuckDB, like if you wanted to do a DuckDB thing, it could be DuckDB.read CSV string transactions CSV path, right? And same thing here. We could read it in with DuckDB or mo.sql. We could do select star from read CSV and then give it, so here we would need like an F string, right? And then you would do transactions CSV path. I'm not going to run them. You know, to prove myself, if I actually did that right, I would run it. But just to show, right, there's many ways. I'll just comment it out and I'll add it into the notebook here so you can see it. Many different ways that you could write this. Let me go back and grab the other one that I had too. Transactions CSV path. Right, just want to show you different ways that you could be running the data. Then the transactions with columns. So this is again a polars thing, but it's converting the string to a date because it's saying the date wasn't correct. But you see that happened pretty much immediately. 200,000 records. I mean, date range, all that's super fast. Both polars, I think both polars and DuckDB do that really well. And now we see actually a DuckDB being used here with describe transactions. Transactions is the schema. Let me see, make sure of that. Yeah. Okay. And then sample data. Right. So no, sorry. Transactions is the table. I was wondering about that. To say transaction table. Yep. Transactions table. Make sure we have that right. Transaction sample. So we're looking here now at a sample of the data. Again, we're using DuckDB still, mo.sql. Select star from transactions, order by date, limit 10. So we have our ordered transactions. Usually I would say limiting 2. This is actually not a great way to filter down results as we talk about different things you might want to know during SQL, right? So I can leave this note in here too. But limit is a data scanning nightmare because limit's the last thing to happen in the order of operations here. So you're going to scan all the data and then you're going to only return 10 rows and you're going to be really confused as to why you scan so much data. And that's why, right? So careful with limit, but it's a good way to be able to do some of this work. Now I know in DuckDB probably bringing in like a head operation. DuckDB 1.5 is coming out here soon, and there's going to be a lot of new additions and changes to what they're bringing. Next up, so we have our data here, data loading NYC taxi data, right? So you see here reading the table. So we read in the transactions data, right? Now we're actually reading it, and this is doing pyarrow parquet, and it's actually reading those parquet files directly in. Again, we can read the files directly in from DuckDB. We don't need pyarrow parquet to read those in, and that might be better for you to not have to load in other tools. It's another thing when we're working in enterprise data sets and enterprise environments, right? We don't want to just load in this just to read, right, a parquet. If we can keep DuckDB and just do everything in DuckDB, it keeps our Docker sizes smaller. It's very helpful. But you can see here we did load in the taxi data, and it's showing here the path. But again, right, this path will be different for you. When you run it, it's not going to have my name. If it does, we're twins and you should call me. Next up, we're going to go ahead and take a look at some of the summary statistics, and this is doing mo.sql, and you can see this is really just super nice because it's SQL code, written in a Python notebook, right? You're also writing Python code in, and that's a kind of point of this notebook, is to show you like how much we're doing between both Python and SQL, and how we're kind of able to just flip between both of them. I mean, look at that. Taxi Jan and Taxi Feb are getting loaded in as SQL tables, and they were actually stored as Pyaro read tables, right, from a Parquet file. So I mean, I read them in as Python objects, and here I'm reading from them as if they were tables in DuckDB. It's insane, right? Like how easy it is to work with both of these. It's a really important call out there. Then next up is you see the CTE. Okay, so this is what we call a CTE, right? And we'll talk about this more later, but it just means we have a with statement. We define like a temporary table. We do something, and then we use that temporary table later. So CTEs are very easy, and they're so much easier to read too than our alternative of doing something like this, right? And how are you going to tell me that doesn't just look like crap, right? I mean, like, we got to read it from the inside out. And then what if we needed this same type of statement later, right? It would be very difficult to do, impossible, really. And it would also be a lot more code. So we've got that. We've got our 5.9 million total trips. We've got our earliest date, latest date, average fare, average distance, and unique days. Window functions. So basic examples of window functions. First up is a row number. Row number is just going to be sequential numbering for our rows. And so you can see, I don't know why, but I got very confused by window functions when I was starting in data started with Python. So it's probably why I was trying to read like window functions in Python and R before I read them in SQL. I think if I had read them in SQL first, it would have made a lot more sense. But as you can see here, we have row number, which does what it says it does, row number, over. So we're going to define like a scope of which we need to look over to figure out how to create these row numbers. And then we're going to partition by region, which just means group by. Like, just partition is just a really confusing word for group by. So grouping by region, ordering by the date. And so what does that look like, right? It's going to alphabetize. Well, not going to alphabetize anything here. It's going to group all the regions together. So, like, let's actually run this just to see what the regions actually are. Okay, so east, right? So east region, everything in east region is then going to get row numbered by their date, right? And if they have the same date, then they will get they will have similar row numbers, right? Hold on, let me backtrack that statement. They will all have different row numbers with row number, because row number needs to be unique. Now row number doesn't actually mean anything in this scenario, right? Because we're ordering it by date, but things in the same region on the same date can have different row numbers. So they don't particularly mean anything at this point, other than, right, just knowing that, okay, everything in the east region is going to have like its own ranking, right? And then ordering by date with a row number where it always has to change, right? Is that necessarily the right way to go about it? You know, who knows? But this is row number by region. Next up makes a little more sense is the row number by amount. So as we can see, there's no partition. So actually everything in the data set gets its own row number, and we're going to have as many unique row numbers as we have rows, since there's no partition by, it's going to be a 1 to 5,000 or 1 to 200,000, like our example is, right? Where the previous row wouldn't necessarily go up to 200,000 because it's grouped by region. This one is not grouped by region, so we'll have a unique row number from 1 to 200,000, or 1 to n being the linked number of rows in the data set here. And this next one, and you can see the order by is price times quantity descending, which means if you had the highest price times the highest quantity, that would be number 1, right? And then from there, we're going to go down. So order by price times quantity descending is row number by amount. A really great way to kind of filter and see who are biggest spenders. All right. That sounds good. Nothing crazy here about syntax or anything. I'd say, like, watch out for dates, right? Dates can be really challenging. Hopping between systems, right? When you're working in DuckDB, maybe you can write your dates one way. When you're working in Snowflake, you can write your dates another way. Like here in Snowflake, you could do something like date. And then that would work to make sure it's being parsed as a date. I think you can just leave it like that too. It's fine either way. In other tools like Postgres, MySQL, SQL Server, everything's going to look different, right? The way you actually need to write your dates out. So just be careful of dates and making sure that those are happening correctly, and then note your order by region and date. So, this is going to alphabetize by region. It's going to order by alphabetized region and then the date within that region. So it doesn't shock me here that we're seeing all Jan 1 and we're seeing all East, because East is the first one in terms of the letters. North, South, East, West. East is going to be the first one. Key insights were numbered by region. Is just sequential numbering within each region by date, and then the row number by amount. You can see, notice how each row gets a unique number even for tied values. All right, rank and dense rank. These are two really interesting ones and have subtle differences that are also really important to understand. So rank, if we look at order by transaction count descending, right? What rank is going to do is it's going to say, okay, if I have first, second, and third place, but they're all tied, right? Then they all get 1, right? They all get the same value. And then next is fourth place. In rank, we're going to have 4 because it's the fourth element to show up, and it should be rank 4. But dense rank says no, really, it's actually rank 2 because it's the second unique element to appear, right? Rank is going to say it's the fourth element to appear. Dense rank is saying it's the second unique element to appear. So dense rank says it's actually second place, whereas rank is saying it's in fourth place, right? So these are two. Those are two different ones. Dense, the way you can think about this too is like dense. It keeps them dense. It keeps the numbers tighter, right? So that's why I think it's called dense rank versus the rank, right? So rank allows gaps. Dense rank keeps everything tight, doesn't allow for gaps. Sorry. And then the intile or the quintile, right? So this 5 here, we're gonna get the 5th quantile of whatever it is we're looking for. In this case, it's transaction count. Right, so we're going to go look at the 5% mark of transaction count and see what that number is. But if we wanted to see the 95th, then we see the 95th. In this case, 5th means what you might think when you think 95th because of the descending. Right, so that's another thing to keep out for. If we flip this, if we just got rid of this, it would become ascending because the ascending is the default. And then you'd want to put 95, and that would make it the same. Right, so that's also something important to note. We'll run this code, and we will see here we have our rank. So customer ID has a total spend of $869 with 14 transactions. All of these ranks are transaction count ranks, right? Not taking into the total spend. You can see the total spend is varying a lot, but you can see that the transaction count here is 14, 14, 14. Now, if you look here, you'll see 111, 4, 1112. I actually didn't look at this too closely before this video, so I just got lucky that was how that was. You can see the rank with gaps is 1 and then 4 because it's the fourth element, and then dense rank is saying no, but it's the second unique element, so it's second, right? So I hope that makes sense seeing it. And quintile is 1, right? Order by transaction count descending is quintile. So we're in the first quintile here of spend. And so what this actually did is this created 5 buckets, right, over transaction count. And if we got 14, if we assume the minimum is 1, then we have quintile. We have 5 unique quintiles between 1 and 14, which would be like 2.9. Right, so transaction, because I would expect transaction count 12 to have quintile of 2. I don't know if I have transaction count 12 showing up. I don't. I do, but it's still showing is 1, so probably quintile 11 moves down to 1, but we have a limit on, limit of 20. So let's pull our, let me make our limit like 1,000. Shouldn't take that long. I've been proven wrong. Interesting. Let's find out. Let's look at that together. This is a thing about where we're always allowed to be wrong. In tile, we're going to go DuckDB. I feel like this is something I should know. But oh. Window functions. We're going to look in here into I want in tile. There we go. Number of buckets. Yep. So 5 buckets. Nope, but that is exactly what I'm interpreting it as, is number of buckets. Define the partition as equally as possible. All right, so let's jump back to our notebook. Even at 10, we have quintile 1. Interesting. It might be using row numbers as well. In order to find out, actually, I do want to find out where the first, or what the minimum transaction count is by each quintile. So I'm going to go ahead and solve that right now just so I can like answer my question and get myself out of this, right? So I'm going to turn this, I don't know if I need to do this, but I'm going to go ahead and turn this into another CTE with previous final, I don't know, as, right? And I'm going to jump this out. Okay, and then select, I want transaction count. No, I want quintile. I want quintile and then min transaction count. There might be a faster way to do this too, but this will help get me out of like, why did that happen? And then group by quintile. Get rid of that limit from that one, and we're gonna run this. Let's see. Oh yeah, you don't put it. I'm silly. You don't put a second with there. Reference column is not found in with clause. It's not is quintile. Candidate bindings, quintal. Got to learn how to spell. Yeah, okay, so it's using row counts, not, and I'd probably, had I read the documentation a little bit closer, I would have seen that. It's using row counts. Yeah, there's a different way to do what I was talking about doing, probably. I mean, might be nth value. No. There's a different way to do what I was thinking about in my head that this was doing. But this quintile, yes, is doing it with row counts. So it's, if we did the, let's do count distinct customer ID here. Yeah, it makes a lot more sense. So you see the customer IDs are all the same here. So if I'm just being stupid, that's the difference between a quintile and a quantile. We'll see if that's actually what's going on. Google's gonna do a little AI thing here. No, I don't really. Yeah, percentile versus quintile versus quantile. Quintile range from any value to any other value. It's just gonna break them up. Percentile, right? Well, no, it's all kind of the same, right? Percentile, quartile, it's just different ways to refer to the numbers. I'm going to go ahead and chalk this up as go ahead and message me if you've got the right words for this. Seem to not be having the right words for this scenario, but as we can see, pretty easy to work around, find the data, and these things are running pretty fast. So I'll pop out of what the differences is between intile, quintiles, quantiles, and all the different ways to break apart our audience groups. But just that's something else we can do in DuckDB, which is a lot of fun. Next up, we're going to do window aggregate results. So the thing we want to look at here is running totals. So this one's really interesting, right? We're going to look at the sum of revenue ordered by date rows unbounded preceding, which means we're going to take our current row and we're gonna look back in history, right, based on the group by, but there's no group by here. We're gonna look back in history to the first row that applies to this group. That's it. Rows unbounded preceding. There's no rows preceding the current row that we need to cut off. That's what that means. And next row is the same thing. Over order by date, rows unbounded preceding is cumulative transactions. So we have revenue, we have transactions. Next up, we have a moving average of a 7-day window. So you're going to see daily revenue ordered by date, rows between 6 preceding. So now we have a preceding. Now we have a limit. If we can go 6, we can take the current row, then go 6 rows back. So it's 6, including the current row, which will be the 7-day window, right? And this is how you're locking off and saying, I only want to look between n minus some amount and n. N is inclusive. You could add another thing in here to say like n minus 1, n plus 1. Different things we could do here with this to catch, right, other scenarios that we might be interested in. All right, we'll run that. And as we see here, cumulative revenue, cumulative transactions. Is it ordered by date correctly? Yes, it is. So you can see here each day things are adding up. Our 48095, 48095, 48095 plus 49530. Right, I'm not in math whiz, but that looks pretty close to me for what those two values should add together as. So that's our window function, and a good idea of why a window function would be important. Next up, like I just talked about there, was the n minus 1 and plus 1 type things. So this is a really easy, elegant way to get those. We're going to lag, which, as you might be able to think, lag is going to go backwards, or it's meant to go backwards. So we're going to lag revenue 1 month back, which would, we're saying here last month's revenue. We have to order by month because it's a window function still, as previous month's revenue. Monthly revenue minus the same thing, right? So this right here is, you see, it's the same thing from the line above as revenue change. So we're calculating our changes in revenue. I know some people might be interested in those numbers. And then we see here again that lag. That lag is mentioned here a couple times as a revenue change percent. Next month preview is lead revenue. 1 is next month, net preview revenue. Now, of course, this would be great if we always had next month's revenue. We're not going to have next month's revenue. But when we're doing historical analysis, we do have things like this, right, that go back and forth. But I would say lead is typically better for like leading indicators. If we have, predicted something into the next month, then we want to use that as an indicator to get the value of the next thing. Then lead is great for things like that. First value within a group. Right, so first value, monthly revenue, ordered by month, rows unbounded preceding as first month revenue. Right, so rows unbounded preceding. Again, we went all the way to the very back, and we got first value. So that's like, and then, the power here would be if you put a partition by in here, you could say, I'm getting the monthly revenue for each group of something ordered by month. So I know I'm always getting the earliest month. So if you want to, like, say, from the first month until current month, this is how much change we've had. Or, the last month, monthly revenue. You could lag it. You could last value it. Either way, right? It just depends on the data that you have. And as we'll see here, we had a previous month revenue. There was nothing in the first row because there was no previous month. Hope that makes sense. And then we're calculating revenue change each month. Seems like we're pretty decent here. What do we have? I feel like we could be doing better. All right. Advanced window functions. We've looked at those. Lag, lead, first value, and last value. All right. We're going to do some more specific DuckDB things. Qualify clause. This is also a Snowflake thing. A lot of tools, I think, are adapting the qualify clause. So earlier, I created a separate CTE to do something qualify is kind of the reason you don't need to use a CTE in a lot of situations. So if we just look down here at this other example from traditional alternative, right, you would see select star from a subquery, give the subquery the ID, like an idea of what this is, and then rank less than or equal to 3. Rank is coming from here, which is coming from inside a subquery, and then we're trying to filter the results of the subquery. You could always do this with a CTE, but this is kind of the situation where I might use a subquery, right? When I'm immediately just filtering out the result, and I just need the subquery so I can do this. So we don't need the subquery anymore. Depending on the tool we're using, you can run a qualify, and then a window function. Normally, window function will come after that. So this one, rank. So as you remember earlier, it's a spaced rank. So we're gonna have less results in this than if it were a dense rank. Something important to consider and think about. Partitioned by region over by total spent. All right. So if we had 3 people tied for the same amount of total spend, only those 3 people, well, really anyone with that amount of spend. If we had 3, if we had 7,000, all of those people would show up. But as soon as it goes down by 1 cent, the next person is not showing up. Whereas in the situation of dense rank, right, the next 2 unique values would show up after that first one. So qualify is really powerful because it means we don't have to write like additional code and additional CTEs. I think that's just really, again, we're putting the joy back into some of these things, and not having to write unnecessary subqueries, unnecessary CTEs. It makes things more readable, and just a lot more pleasant to work with. So there's that. Filter, clause, conditional, aggregates. So let's run this really quick so we can just talk about this. This one's pretty wild, right? This is definitely not anything you're going to see in a lot of other places in SQL world. So we're counting, and then we're using filter is kind of like a window function, and then we're giving it like what we want the count of inside of this. So it's really wild, right? Because then you have all these different columns for promo 10 count, but you didn't have to do anything crazy. It's just doing the filter like you're doing a window function, and then saying what do you want to filter on, and then that's the column, and then you've got region, right? Total transactions, and you're grouped by region. So now you've got how many promo code were equal to promo 10 in the East region. 8,347 of all the transactions, right, that occurred. So that's pretty wicked. I think that's really cool. And again, that's just most like doing that a couple times. And you can see like the revenue on the promotions in the groups. In another world, it might take a lot more code to write something like that. So pretty simple, pretty beautiful. All right, next up is statistical functions within group, right? So we can also do statistical functions here. So let me find, let's see. Yeah, okay, so we're within the quartile group, right? Quantile, multiple quantiles, quantile continuous amount, 0.25, 0.5, 0.75. Okay, so this is where the quantiles are going to come back and get me again. But if we look here, we see that quantile continuous for percents. So what this is actually going to do is break out into, like if you see here the P equals 0.25 is I'm going to get the first quartile. P equals 0.5. I'm going to get the median, right? So quantile continuous amount in 0.25. That means I want the first quantile, and I want the third quantile. And remember, it's by, I'm telling myself to remember, not you. It's by row numbers, right? And by the amount of transactions that fall into the quantiles that create that, right? So the quartiles are being created, spread measures. So standard deviation, range, all the really useful statistical things. You can see here you got your P1 and your P99. We use those a lot too. All right, so you run these. You see here, you got your mean, you got your median. Notice they're way off. Be careful of that in the wild. That can come back to bite you a lot of times. And even your Q1 and Q3, right? Just have a good idea. I think I would calculate your IQR. Here, have a good idea of what your IQR is compared to your median, compared to your mean. That tells you a lot about how your data is distributed, and gives you a kind of a quick way to think about some of these things. So you've got your range, your min, your max, P1, P99. So again, a really big difference between your P1 and your min too. I think generally, and even from max to P99, I think there's pretty large differences there. All right. DuckDB statistical foundations. So I'm definitely not the strongest statistician, won't ever claim to be or try to be, but some of these things I think are important to know when you're just trying to do a quick analysis of your data, right? You want to understand how the data exists and how it's structured. Next up is a CTE versus subquery performance comparison. So the decision framework for me is pretty damn straightforward. It's don't use subqueries, but you know, everyone's gonna have their own way they want to do things. So let's look at the CTE approach, right? This is calculating like a bunch of stuff, right? I mean, you've got low value, low frequency. This is like a really common customer metric, like marketing data science thing. We've got a load of low value, low frequency customers. High value, high frequency, like these are like our money makers, but we want to turn like our high value, low frequency, we want to turn them into higher frequency and turn them into our big money customers. Our low value, high frequency, right? Maybe we got some brand loyalty there. We want them to stick around. So anyway, this whole chunk of code is doing like a lot of really interesting things, right? It's breaking up total spend and transaction count and kind of creating a group. It's all pretty straightforward, but it's useful just to give us language to think about customers. Right, and that's where CTEs are helpful. Now, we're going to do the same thing here with subqueries, and I don't know if you're seeing this, but it's already less fun to look at. This is it's different stuff we're calculating here, so I'll drop down and okay, did it run? Hasn't run yet. Nope, right in there. So different stuff we're calculating here. Some of this is needed because it's claiming to be simpler operations. If we look here to see the rounding, the round here is actually price and quantity minus an average of the price and quantity from T2. So this is actually saying like for each customer, because we're on customer ID, for each customer, take their price times their quantity, and then take that from the difference from their average, right? Because we're calculating the average, and then we're joining the subquery to the actual query result, right? So it's actually a correlated subquery because it actually needs to know, information from the outer query in the inner query. So these are, to me, like horrific nightmares to write. I don't write them a lot. I don't really have needs for them a lot. But when they do happen, right, they're frustrating to write. Next up is the non-correlated subquery, which just means it's self-contained. It doesn't need any information from transactions, or it doesn't do the. Hold on. Well, it definitely needs information from the outer query. So again, I'm wrong again on that one, because T dot region right there. But in what I understand, correlated and non-correlated subqueries just mean does it need anything from the outer query or not. Again, I'm open to being wrong, but as you see, just subqueries are less enjoyable to write. Let's make sure about that. Diff between, and then you see all these ads on Firefox. Gotta figure out how to get rid of those. Correlated and non-correlated subqueries. I'm open to being wrong and having to Google things sometimes. All right, let's check it out. Yeah, I mean, definitely definitely performance nightmares sometimes when you have to write one of these. All right, so here's a non-correlated subquery. It's just getting the max and returning a single value. And then this correlated subquery is actually doing the join. So I think the notebook is potentially wrong. Did have that right. Right, count of customers' previous transactions. This is, again, it's another subquery inside of this main query. So it's just, it gets like really not fun. It worked, but I would definitely not really recommend it. So correlated operations are row by row. Sure. Performance comparison. CTEs are better. That's the performance comparison. I wouldn't even say like subquery for most of these. Maybe the row by row comparison, right? But I would say CTEs pretty much across the board. Yeah, again, there are times when a subquery makes more sense, but it's like more so breaking the rule than the rule, right? The rule should be CTEs. And once you know the rule, you can break the rule a little bit more. Here's a simple CTE and the equivalent. Okay, so what we're saying here is this was 31 lines, right, in this cell to write it like a CTE. And here it's, we get down to line 22. Of course, there's some scaffolding with the mo.SQL here around it. It's just trying to say this was less code. Again, I would still venture to say that this is easier to debug because you can grab this one, you can grab this one, right? You don't have to pull them out and have them be nested inside of themselves. This is not important. It's just doing some formatting for later on. And then we're actually going to do an explain call for, so this query runs. So explain calls are really interesting. Wow, I'm already at 43 minutes. That's crazy. Explain calls are really interesting because they get to show us like how the code is going to get executed. And so you see the code and the data in front of you here, the customer ID, the transaction count, the total spend, average per transaction, all of these things. When you need to debug, say this starts like acting up, right? And it starts not doing what you need it to do. You can run this explain. You literally just put the explain in front of the query. And then this is where I said earlier it didn't matter because it's just doing some formatting stuff. But this is the query that runs, right? And DuckDB gives us this explain. Snowflake has an explain. DuckDB has an explain. Pretty much everyone has explains at this point. Explains, though, important to note, you read them from the bottom up because the top thing is the last thing that happens, right? And the bottom thing is the first thing that happens. So you have to read these from bottom up. So that's why you see the arrow scan, the projections, the filters. Projection happens, you got a row, hash group by, filter, projection, top, right? Tree structure view, same thing here, scan, projection, hash group by, filter, and top. So we're doing that. Important to know how the explains work. Here's another explain for the simple subquery. So what did we see here? We saw the explain for the simple CTE. And so this is good. So we're actually getting the explains across both. So you can see we have 1, 2, 3, 4, 5, 6 steps in the CTE. And here in the subquery 1, 2, 3, 4, 5, 6, 7. So we had just one more step in the simple subquery that we had in the CTE. So that's important to note too, is like what steps are happening where. So you can see the filter here is a separate step, which I think the filter in the CTE is what we don't have. We do have the filter, but it's total spend over 300. Hold on. Arrow scan, projection, hash group by. Yep. Filter, projection, arrow scan, projection, hash group by, filter, projection, top in. Oh, hold on. I'm only seeing 6. I counted wrong. And here I saw 6 too. Yep. So there's 6 for both. So that's what it's trying to say here is hold on. 1, 2, 3, 4, 5 in the structured view. 1, 2, 3, 4, 5. Okay, 6. So the tree structure view is giving me different amount than the structure view itself. That's important to note there. So here I am seeing 7 in the arrow scan, starting from the arrow scan. So you got arrow scan projection hash, filter projection top. We got arrow scan projection hash, filter. There's not another projection here is what we're having. And we have the second projection here in the subquery. So that's what I mean to say, like, I think the CTEs also just offer better performance. They generally do have fewer steps, even if just by one, right? Even one step could help. So explain efficient scan methods, right? You want to see index scans, not sequential scans. Hash is a great word to see a lot of the times, not all the time, but most of the time hash is a good word to see. Fast for most group by operations and minimal materialization. Right, subqueries avoid intermediate result materializations, and CTEs do come with some cost to materialize those results, because what happens is a CTE, like I said, it's available for other pieces, like, so it's a temporary table that's made available for a short period of time, whereas the CTE or so subquery is immediately like consumed, right? So it's not holding the results from that in memory. So that can be a time where you might need something like that. So CTEs might be less optimal, where you have recursive logic, can't be inlined, and they're referenced multiple times. When they're referenced multiple times, exactly why we want a CTE. So this is not why sometimes the AI generation of these notebooks aren't great. And the real world optimization tips, readability, I do think it's very true, right? Make it readable. Optimize it later, but keep readability in mind always. Measure performance. We have to explain. DuckDB is really great at what it does, so let DuckDB be great at what it does. And then this is just a little Easter egg here is on the pivot. So the pivot is really interesting because you build pivot tables, right, a lot in Excel and things. So here in DuckDB, you can pivot just like you would pivot in Excel. So here we have like an advanced pivot usage. I don't want to spend too much time on these advanced pieces, right? You can cover them in your own time. And then unpivot, you can convert wide to long format, right? So we'll see here our pivoted data. So in DuckDB, right? Actually, so what you're seeing here in the code is like how we would do this in SQL. All right, without DuckDB, right? This is how all of this would have to get built in SQL to build some concept of a pivot, unpivot, converting wide to long, and now the unpivot techniques, right? Native unpivot. Now DuckDB native unpivot, right? It's just unpivot, which is pretty wicked. And then you give it the columns, and then you tell it what to pivot into, right? Name, value, name is region, value, sales, on these columns, boom, done, right? Pretty wild. Idempotency is really important. Idempotency just means I can run multiple things. I can run the same thing multiple times and get the same results every time. So needless to say, insert into is not going to be the same result every time, because as you see, if I keep running, this one has 5. We're going to run and see those 5 rows, right? If we kept running an insert. So what this is not doing, this isn't doing actually an insert at all. It's just selecting distinct, creating if doesn't exist, right? And then here, same thing. We're getting some of those data, and then create table as, right? So create table as, it'll create it. Idempotent operation completed. There's 10 rows because we have our limit by 10. Idempotent table contents. Got it. So really what would happen here in the example of a not idempotent world, right, is if you had like a create table, if not exist as, and then there would need to be like an insert into happening here, right? If there was an insert into happening here, this number would continue to grow, and it wouldn't be a safe operation to make. And that can be that'll give you a lot of headaches later on, because you're going to start seeing duplicate data. So avoid, right, insert into. Most of the time, as you can see here, this is a create table as, or a CTEs as we call it at Snowflake, and it's just what I've been calling it, and that's where I learned the term at Snowflake. Create or replace table, this table name as, and then give it the query. So this is when you're building it in from other data, or in DuckDB, you could load it in from a CSV, from a Parquet, create or replace table as. Pretty wicked, right? Idempotent table contents, and then this is a write-up kind of on what idempotency is, what it means, and then next up is a performance tuning and optimization. So as we can see here, we have early filtering. So if we want to look back at some of these things that we're seeing, right? So we have where date is equal to 20, and that's in the first CTE, 2024-0101, right? First CTE, group by, having count. We're filtering after the aggregation. So with the thing about CTEs holding data in memory for a short amount of time, the more filters you can put on those CTEs just to keep less and less data in memory, it's great because it's going to make all your operations faster. So those are the two important things to know, right? Filter early and filtering after aggregations, because you're usually going to be looking for a specific thing within that aggregation. So I think that's important to know, right? And then each CTE builds on the last one. So you can see customer metrics here, which was built here. It keeps things in order, and it also is just easier to read and debug later, part of it. So query optimization strategies. There's a lot of examples in here. I like the formatting of this. Here it's filtering after the aggregation. Here it's filtering before and after the aggregation, which is what we want. We want to remove things as easy as possible. Try not to put like function references in the where, because a lot of times, even if it is possible, it makes the compilation step a lot harder on the optimizer, and a lot of optimizers are going to suffer here if you're putting functions in the where. And now I know a lot of us will do it, and it's very common for us to do it, I think, data engineers. But if we can find a better way around putting a function inside of the where, that'll be safer for all platforms, right? Whether your specific platform is going to search or is going to support clustering and partitioning when you have something like this, a function on a where. To be TBD, Snowflake I know supports a lot of things like this, especially when we're working with dates, because this is kind of the most common use of putting a function on a where, is when you're working with a date and you want to pull the year from it. This is a really common use of it, so we've kind of beefed up our support for things like this, or Snowflake has. But across platforms, it is better to use a range condition for the index. Group by most selective columns first. I think this is pretty nice and pretty interesting. So the customer ID, right, being the most selective. Now, I would say we'll have to be careful with this, because really your group by is going to highly depend on the question you're trying to answer. So I'm not even sure that I could recommend that, right? Because what the question is answering here is it's saying customer ID. So immediately I'm saying, okay, the answer I give needs to be at a customer ID level. So I think this, again, downfall of some of this AI generated content. I'll go back through and look at this notebook too, just make sure I agree with the things that are going on here. But it really does depend on the questions being asked. Next up is region and product category. So this being saying like, hey, for each customer and region, right, what were the different product categories for each product category for that customer, for that region? Like, what did they do? So depends on if you're asking that question, if you need to answer it. CTE for subquery choice, just use CTEs. Don't think about it too much. Subqueries, if you're like, if you can 100% say that the subquery is what I need, put that subquery in there. But so you generally don't need it. Debugging methodology, yeah, this is debugging methodology demonstrated. Yeah, this is pretty helpful, right? Validating your base data, making sure that data you're looking at is the data you think you're looking at. And then, yeah, building incrementally, adding in one thing at a time, and then slowly adding complexity. And then other tools like DBT are going to give us the ability to build like test and things once our code starts getting complex and starting to look like this, CTEs and formulas and calculations happening. You can also build other types of testing if you're using Python, right? You can do some PyTest stuff, but DBT is really good for some of these things. Check intermediate results, makes sense. Yep, absolutely. I print out intermediate results all the time. Validation and query results. I'm gonna just kind of move on, right? Some of these things I think are, yep. So here's our summary. So here's all the things we've talked about today, right? We talked about window functions. We talked about advanced DuckDB commands. We talked about CTE versus subquery, just use CTEs. We talked about pivot and unpivot operations, idempotency, performance optimization, and of course we based this off of some real data sets, right? So definitely take your time to look through this notebook and understand everything that's going on. There's some really useful information in this notebook. There's a lot going on here, so definitely understand if at any point it's heavy. And then here in Marimo, I'd say I'd also recommend using your variables here on the left. So in Marimo, we can see, like, look at that. Like, we can see the freaking sample and summary idempotency as DuckDB tables, right? Like, that's crazy. That's pretty cool. Test result, transactions, taxifab, jam, and all the Python objects that we saved that we then later referred to in DuckDB. So again, this is like Marimo specific things going on here. You see the packages that we have installed, but Marimo's pretty nice. I don't have any AI things going on in Marimo because I don't edit a lot of my code in here, but you definitely could. It's a really nice tool to work with, so highly recommend checking out Marimo a little bit more instead of Jupyter if you can, because I'm seeing all the different variables I have here, also where they're defined and then where they're referenced later, right? Which is also pretty crazy when you think about it. So everything's up to date here. Whenever I need to, like, oh, where did I like define that thing at, right? Click it and it'll boom, drop me right to where I define performance result in cell 75. So not just cell 75, it's cell 75 row 49 that it dropped me into when I clicked on this. So that's really, really helpful. And they do it in a way which is like, VS Code does that, but they do it in a way here in Marimo where it's less intimidating, I think, for some people to be able to click in there. Live docs. So if you've got documentation, dependencies, right, are also listed out here. It's also pretty cool, right? Looks like it didn't like it when I clicked graph. It's gonna now freeze up on me, but it is what it is, right? We've run through this notebook. I think we had plenty. Don't have time to spare. We definitely had plenty to talk about in the time that we took here. But if you have any other questions on this notebook, absolutely reach out, right? I'm happy to share more about it, reach deeper into something with you. These are all really, really fundamental things to understand. I think we, went a little bit past beginner stuff, which is also important for who the audience that we're hoping to be speaking to is. We don't want you to be thinking about beginner level stuff. We do want you to be thinking a little bit deeper about how can you optimize and how can you write better code. We think this is kind of that next step from beginner into intermediate land, and some of you even from intermediate land beyond are some of these things. I think one of those things, that filter function we looked at in DuckDB, that advanced DuckDB command, the filter, is I would call that definitely more advanced than qualify, but I would definitely call these advanced, right? Just understanding their capabilities, and you can do some pretty powerful things with them, and keep close to DuckDB because they're constantly doing more and more. So again, thanks for your time here. Hope you enjoyed this, and like I said, absolutely reach out. I know we're just at an hour now, but think this is a helpful notebook to walk through, and you can definitely message me if there's anything you need. Have a great day, everyone. We'll see you next time on Saturdata.